Hello and welcome everybody to another episode of Wissenschaft fürs Wohnzimmer. Today it's sitting room science, as we have an English episode tonight, and I'm very happy and looking forward to the talk by Nathan Beech tonight about ocean models and how we can learn from models about the oceans of the future. And I'm also happy to be joined by two other colleagues moderating with me tonight. And so I'm handing over to Corinna.
Yeah, thank you very much. So my name is Corinna. I work also at the AWI. I'm a marine biologist, and my focus is on the North Sea. And we want to restore the once native oyster there. But today it's a different focus, so I'm excited to learn more.
Yeah, good evening. I am Rebecca, and I'm also a scientist at the AWI, but I'm a physical oceanographer, so a little bit similar to what Nathan will present here. But I use observations up in the Arctic Ocean to look at the melting of the glaciers up in Greenland and the general warming of the Arctic itself. I'm looking forward to hearing what Nathan will say about the potential future of that, and if there are going to be any more glaciers to study in the end. So Nathan, no pressure, but we're looking forward to hearing your talk this evening. And so over to you.
Yeah, happy to finally be here. Big fan of the show. My name's Nathan. I'm a PhD student at AWI in climate dynamics. I'm gonna give a little presentation today. So, shall I jump right into things? All right. Yeah, so as I said, I'm a PhD student in climate dynamics at AWI, and so the presentation today is going to be on the impacts of climate change on ocean circulation using the climate model that we typically use here at AWI called AWI-CM. So first, we should decide which regions we're going to consider critical today. And the answer to that might not be immediately apparent because there's a lot of different ways to look at the ocean. But I'm not going to be talking about biology or chemistry or economics or anything because I don't really know anything about that. If we considered all of these factors, then we might just say it's all critical. So we can change the question a little bit and say, in terms of ocean circulation, which regions are interesting, which ones are highly active? And so the map that you see here on your right, this is ocean surface velocity simulated by AWI-CM. And we can probably see right away that there are some regions where there's more going on than other regions. And these are generally the paths of major ocean currents like the Gulf Stream, the Kuroshio Current, the Agulhas Current, the Brazil and Malvinas Current, and the Antarctic Circumpolar Current, which I will call the ACC for short. And so now that we know which regions we're talking about and we know that there's something going on there, we can probably ask what exactly is going on there. And so I've zoomed in on one of those regions. This is the Agulhas Current that you can see here. And what we're seeing there is called mesoscale ocean eddy activity, or eddies. So these things here are actually some famous eddies called Agulhas rings because they're rings and they're coming from the Agulhas Current here. But what is that exactly? Well, it's defined as ocean flow deviating from typical conditions. And so if we pick a region of the ocean, like right here, and we look at our scale down at the bottom, then typically there's not much going on there. Typically the surface velocity is about 0, but every once in a while an eddy will come along, like you see here, and it will change the surface velocity. And not only that, this isn't just about velocity, it can also bring things with it, like heat from different parts of the ocean, nutrients from different parts of the ocean, it can cause mixing in the ocean, which will facilitate gas exchange. So gas from the atmosphere can be dissolved in the ocean. And an important gas that can be dissolved is carbon dioxide, which, as you probably know, is involved with climate change. And so the oceans have actually absorbed quite a lot of the carbon dioxide that humans emit. And so, although I said that I'm not going to be talking about biology or chemistry or any of that, we can actually relate ocean circulation and eddy activity to these different fields. And that's one of the things that makes ocean circulation really interesting to study. Now that we know what we're talking about and we know where it is, we can ask ourselves, why is eddy activity where it is, and what causes it? And so it's a bit of a technical answer here, but essentially when we have ocean currents, we have a lot of water moving along a path in the ocean. And so there's a lot of energy contained in that. And when that energy is unstable, and it often is in the real world, then it can kind of branch off of the main path of ocean circulation and whirl and swirl around, and that's essentially what an eddy is. So now let's start to talk about climate models, because that is how I'm going to bring climate change into the picture here. One of the things that climate models do in order to simulate the whole world is to divide the world into smaller chunks and then simulate conditions in each chunk in order to define the world as a whole. So climate models might say that in this box here, it's 10 degrees Celsius today. Over here, it's 5. Down here, we've got ocean velocity of 1 meter per second in this direction. And over here, it's another direction and another speed. And then tomorrow, it can all be different again. And that is how we simulate the climate in time using a climate model. And so now let's bring back eddies in climate models. Say we've got an eddy here, and we've got a grid that's about this size, then all we can really say about this eddy is something like that, because the climate model is only going to define the world in each of these chunks. And so instead of seeing an eddy here, we just see the average of, in this case, it's surface velocity, but it could be any other variable like temperature, something like that. And so with a grid of this resolution, we can't really simulate eddies. And so the rule of thumb when we're talking about resolving eddies in a climate model is that we need a resolution of 1/2 of the local Rossby radius, which just means the 1/2 of the radius of a typical eddy in a region. So if this is our eddy that we're going to talk about here, and this is its radius, the distance between the center and the edge, and then that's 1/2 of the radius, then the grid resolution, the minimum resolution that we want to simulate this eddy is about this right here. But if we're going to define the resolution that we need in order to simulate an eddy based on the size of the eddy, then we also need to know what the size of eddies is in different regions. And that's what you're looking at here. This is the local Rossby radius, so the radius of a typical eddy in each of these regions. And we can see that near the poles, the radius is quite low. It can be less than 10 kilometers, whereas around the equator, it can be pretty high, greater than 80 kilometers. And so bringing that back into climate models and the grids that we use, the traditional modeling approach is to divide the world into rectangular cells that are pretty much the same size wherever you go. Not always, but pretty much the same size. And what makes AWI-CM, the climate model that we're going to be talking about today, unique and interesting is that we don't use that approach. Instead of rectangular cells, we use triangular cells. And so here you can see a zoomed in version of the ocean grid from AWI-CM. And you can see that the triangular cells near the bottom of this zoomed in portion are larger than the ones at the top. And so we can vary the resolution of the grid based on where we need a higher resolution. And another important thing to point out is that with these triangular cells, all of the corners are corners, no matter which triangle you're talking about, and all of the sides are sides. Whereas if we were using a rectangular grid, then we couldn't have the corners match up and maintain and change the size as we go. So this is what allows us to have a variable resolution grid. And so there are different ways that we can vary the resolution of the grid, but in the setup that I'm going to be talking about today, this is what it looks like here. So in dark green, you can see regions that have a grid resolution of less than 10 kilometers. And then these bright areas have a resolution of greater than 70 kilometers. And what that means is that we can resolve eddies of different sizes in different regions. So put that in terms of the radius of a typical eddy in each of these regions, and remembering those critical regions that we defined a little earlier. If you forget what they were, then there they are again. We see that the radius in our model, or the resolution in our model, is approaching the threshold of 1/2 of the local Rossby radius in these, or exceeding it in these regions of high eddy activity. And so that's what allows us to simulate eddies in key regions. And so how do we perform when it comes to that? Well, on the left here, you can see eddy activity simulated by AWI-CM. The variable here is eddy kinetic energy, but we don't need to get into that or how it's calculated. All we need to know is that it's an indicator of eddy activity. And on the right here, you can see the same thing, but as it's observed using satellites. And what we see is that in these key regions, we reproduce eddy activity pretty well. When we go outside of those key regions where we sort of sacrificed our grid resolution in order to focus on the more important regions, then we don't reproduce eddy activity quite well, but that's all right because we want to focus on the more important areas. And so finally, to bring climate change into the picture, how a climate model can simulate climate change is we start with the historic period where CO2 levels in the atmosphere were pretty much unchanged by human activity. And then we tell the model how much CO2 is entering the atmosphere based on how much CO2 we know humans emitted in the past. And we do that all the way up until the present. And then, of course, we don't know how much CO2 or greenhouse gases are going to be emitted in the future, but we can say, all right, assuming we mitigated emissions a lot, then what would happen? Or assuming we don't mitigate emissions at all, then what would happen? And so the scenario, the climate change scenario that I'm going to be talking about today is one in which CO2 levels are roughly double those of present day values by the end of the century. So it's a scenario where we would have to mitigate some of our emissions, but not all of them. It would still double by the year 2100. And so the variable that we're looking at on this graph is global temperature. And so you're probably already familiar with what would happen to global temperatures in the context of climate change. They get higher. But what you might not be so familiar with, and what's still more of a question, is what happens to eddy activity in the context of climate change. And so that's what we're going to be looking at today. But before we move on to that, the one last thing that I want to point out is that there's more than one line on this graph here. There's actually 6 lines, and that's because we don't just model everything once. We actually model things 5 times, the same conditions 5 times. And we do that to make sure that the changes that we're seeing aren't just random or something weird is going on. But since these changes are so consistent when we model them 5 different times, we can rely on them better than if we just had one example. And so the darker black line in the middle is just the mean of all those simulations, which we call ensemble numbers. And so, as I said, we probably know what's going to happen to temperature in the context of climate change, but AWI-CM now allows us to see what's going to happen to eddy activity in the context of climate change. And that's what you're looking at here. So this is the difference between eddy activity in the early historic period and the end of our climate change projections. And so where you see red, then the climate model is predicting that there will be more eddy activity in this region in the future than there was in the past. And where you see blue, we expect that there will be less eddy activity here in the future than there was in the past. And so already a few things should probably stick out to us. One is that the eddy activity along many of our major ocean currents, western boundary currents, seems to be shifting poleward. So if there's blue closer to the equator and red closer to the poles, then we have eddy activity shifting poleward. And that's interesting because it's something that's already been observed and something that's been predicted in the context of climate change by other scientists, in fact, some other scientists at the AWI. And another interesting thing, though, is that in this climate model, in these simulations, the Kuroshio current right here is an exception, so we don't see it shifting poleward. So it'll be interesting to see what actually ends up happening there, because we have a bit of a contradiction. So now let's zoom in on the different regions, and we'll go on a bit of a global tour of critical regions for ocean circulation and look at our projected changes in eddy activity. So this is the Gulf Stream. You've probably heard of it. It's what keeps Northern Europe warm. And you might not be able to see it from the map here, but we actually expect a decline in eddy activity in the context of climate change. So that's what this line is here. This is our ensemble mean, the black line. And we see after the present day, 2020, around here, we start to see a decline in eddy activity. And so that's already an interesting result, but we can go even further and say, why is that happening? And the answer could be the widely anticipated decline in overturning circulation in the Atlantic, or AMOC for short. That's something that's been projected by many climate models, including AWI-CM, which is what you see on this graph here. But you might be asking, what is AMOC exactly? And so the very short answer is that it's thermohaline circulation. So around the equator, it's warmer than it is at the poles. And so the water there is warmer. And that means that that creates a gradient between the equator and the poles. And the warm water in the tropics and around the equator wants to escape to the colder regions. And so it creates a current that goes through the Gulf Stream. And then that pushes cold water south towards the warmer equator. And so why should that decline? Well, again, the very brief answer would be an influx of cold, fresh water at the surface of the North Atlantic, which would just back up the whole circulation system. At least that's what's theorized. And that could result in less eddy activity since there's less water flowing through this current. So that's a lot of speculation, though. Let's put that in the context of the observational record that we have from satellites. And so that's what you see in red here. And the trend of this red line here, as you can see, is increasing. So that doesn't match up with the decline that we project in the long term. But then if we just look at the model data during the observational period, so that's what this blue line is here, we can see that there's actually not a lot of change in the model data during the observational period, which is about 30 years. And so what that suggests is that even though we predict a decline in the future, we don't expect that it would be observable yet. So it could still happen. Let's move on to the South Atlantic. This is the Brazil and Malvinas currents. They're in the South Atlantic as opposed to the north of the Gulf Stream. And as you can see, we project a substantial increase in eddy activity here. And the reason for that could be the same as in the North Atlantic. It could be AMOC decline. And the theory here is that the heat and energy that used to escape the tropics through the North Atlantic, through the Gulf Stream, as that declines, then increasingly that heat will take a southward route to escape from the hot equator. And that's exactly what we see when we sort of double check that with the rest of the model data set. So we don't just have surface velocities in the model data set, we have all of the information about the whole globe. And so what we can see is that the Brazil current, which runs south around the coast of Brazil, we see an increasing volume transport there. So more water is passing through this current in the context of climate change, while the eddy activity in this region is increasing. So again, let's put that in the context of the observational record. In both the modeled and the observed data sets, we see a slight increase in the eddy activity over the past 30 or so years. But interestingly, when we compare the modeled increase during the observational period to the modeled increase over the rest of the 21st century, we see that in the future, the increase is greater. So we expect it to accelerate in the future. And next, you can look at the Kuroshio current. Now, this is off the coast of Japan in the North Pacific. And in this region, too, we expect an increase, or we project an increase in eddy activity. And so the conclusion, or the hypothesis that we have for the previous two regions that we looked at is, as more water is moving through this current, we get more eddy activity, more energy and more eddies as a result. And as it turns out, the volume transport, so the water moving through the Kuroshio current, is also expected to increase in the context of climate change. And so we can double check that theory with the model data set. And as you can see here, we also project an increase in water moving through this current, which means more energy and more energy that can be converted into eddies. And again, we can ask ourselves why that is. And again, very simply, we know that climate change is heating things up on Earth, but it's not uniform throughout the globe. And as it turns out, upstream of the Kuroshio currents, things are getting hotter because of climate change than downstream of the Kuroshio currents. And that means that there's a steeper gradient between upstream Kuroshio and downstream Kuroshio. And that means that more energy wants to escape this southern region through the Kuroshio current, and that means more water goes through. So again, let's put that in the context of the observational record. Again, we see that there's a slight increase during the observational period. And again, we see that over the rest of the 21st century, after the present day, we expect a greater increase than we see now. So we expect the rise to accelerate. Now we can look at the Agulhas current, which is off the southern coast of Africa. And as you can see, there's not a huge change in the magnitude of eddy activity. The value here stays pretty much consistent over the course of the simulations, but there's still a lot that we can discern just from sub-regional changes in the Agulhas current. So in this particular corner of the map here, we see more red than we see blue. So we see more eddy activity, or rising eddy activity. And that is reminiscent of Agulhas leakage. And Agulhas leakage is essentially water that's flowing through the Agulhas current, and then it breaks off the current, and it, in the form of eddies, enters the South Atlantic. And so that's how water from the Indian Ocean over here ends up in the South Atlantic over here. And it typically takes the form of mesoscale eddy activity, which is why we can see it on this map here. But we can, again, double check that with the rest of the model data set, and we see that Agulhas leakage does increase in this model. And we also find from the general scientific understanding of ocean circulation that this is expected to increase in the context of climate change already. And so we can confirm that with these simulations here. Another thing that we can see in this map is a southwestward shift of the Agulhas retroflexion. Basically, when you see an increase in eddy activity in the southwest corner of this map here and a decrease in the northeast, then we can call that a southwestward shift. And that's something that's associated with more Agulhas leakage, which we just saw. And it's also associated with lower volume transport, so less water moving through the Agulhas current. And so again, we double check that with the model data set, and that's exactly what we find in the model, is that water moving through this current is expected to get less, or it's projected to get less by the climate model. And so we can put all that together just by looking at changes in eddy activity. And finally, we'll put it in the context of the observational record again. And interestingly, we see in both the modeled and the observed data set, so the red is observations and the blue is the modeled changes during the observational period, we see an increase in eddy activity. But throughout the rest of the 21st century, we don't see that increase continuing. So what that tells us is that the model agrees with the observations in that we would expect over the past 30 years to see an increase in eddy activity, but we don't expect that to continue. And the last current that we'll look at is the ACC. Here we see a pretty substantial increase in eddy activity. And what do you know? That's also something that's anticipated in the context of climate change. The reason for that is an intensification of westerlies. So strong westerly winds in the southern hemisphere are expected to get even stronger. And that can give more energy to the oceans and cause more eddy activity. And so looking at the rest of the model data set, we see that there is a big increase in surface winds in the southern hemisphere, which checks out with the rising eddy activity. And interestingly, the ACC is the only current in which the increase during the observational period is consistent with the modeled increase throughout the rest of the 21st century. So what that tells us is that the increase that's already observable from satellites, we expect that to continue at about the same rate that it's going now. And so let's just sum everything up. We started with AWI-CM and we tried to vary our resolution of our model grid in order to simulate eddy activity. And it turns out that it works pretty well in the key regions of high eddy activity that we focus on. Then in the context of climate change, we projected a lot of significant and diverse changes in the different currents that we looked at. And we were able to connect those changes to a broader scientific understanding of ocean circulation, so what other scientists have already predicted. And we were able to find reasons for those changes in the rest of the model data set, like changes in wind, changes in ocean circulation in general. And finally, in most of the regions that we looked at, it doesn't seem that the satellite record is representative of the long-term changes that we project just yet. So yeah, now I'm happy to take any questions if there are some.
Great, thanks a lot. I love this animations. They always look like, yeah, much more fascinating than those pictures that are not moving. So yeah, thanks. There were actually questions in the chat, and we're happy to start the discussion. If you would unshare your screen, then I can make the announcement for next week, because what I forgot to mention in the introduction was that today it's the 99th episode, which is a great number, and yeah, still unbelievable that we're having that many Thursday evenings already together. with our viewers. But yeah, even more exciting that we have the 100th episode coming up. It's not next week because next week is a public holiday in Germany and we will skip that one, but in 2 weeks, so which would be then the 2nd of June, we have a special guest. I hope you can see that now. Yeah, so for our 100th episode and the second year anniversary, both at the same time celebrating, we will have Professor Mujib Latif with us. So yeah, I will just quickly switch to German because his talk will be in German. So ja, nächste Woche, in die nächste Episode, also nicht in nächste Woche, sondern in 2 Wochen, wird gehalten von Mujib Latif, dem Professor am Geomar und der Universität Kiel. Und sein Vortrag hat den Titel Nach uns die Sintflut. So he will talk about the big picture and how we can still manage to be, to keep the Paris Agreement target to stay below 2 degrees Celsius warming alive. And we're looking forward to that. So I will stop share my screen and then we can, start the discussion. And I will ask Corinna for the first question.
Yeah, thank you. So back to the modeling data about climate change. We have one question from Zebra Twist, who wants to know, why do the eddies get smaller towards the poles?
So that's a good question, and I can't really answer it properly right now. It's a pretty technical difference. It has to do with the different forces that are acting on water and which ones become more or have a greater effect than the others, and that can change in different regions, mostly with the latitude. If you know the Coriolis effect, it has to do with the rotation of the Earth, but we shouldn't get into that because it gets a little bit complicated. But yeah, it's because different forces have a greater impact on the water in different regions. And yeah.
Thank you. Makes sense.
Nathan, that was a great talk. You made a lot of sense over a very difficult subject. I have been trying to explain another type of model in various presentations, and the triangular grid throws me every time, but you made that perfectly clear. So thank you very much. It was very interesting. There are other questions in the chat, but I'm going to jump in actually, because I'm an observational oceanographer, which means that we put lots of instruments in the ocean, also to measure currents and temperatures. And I know that you use satellite data there to compare your observations with the model, and that looked actually very promising. Do you ever use the in-water observations, for instance, moorings or the Argo floats, to also validate your model?
So I don't. And the main reason for that is that we are in the project that we were working on, that this presentation sort of came from. We really wanted to do a global study, so all of these different regions, and I'm not entirely sure, but essentially satellite data can cover the whole globe, or almost the whole globe, with pretty good resolution, whereas the in situ measurements are just a lot harder to get a good consistent data set from.
Yeah, tell me about it. Yeah, that makes that makes complete sense. Thank you very much.
Great. Yeah, there was 2 specialists discussing. I totally felt that, but sounds still makes sense. And then there's a question from the chat from Supermomme, which is asking why you choose to have 5 repetitions of your model runs. Is there any reason for choosing 5?
So if the question is why exactly 5, then essentially because it's very expensive to run a model like this over a long time period with relatively high grid resolution. It takes a lot of time and a lot of money using big supercomputers. And so, but then having more repetitions increases the reliability of the data set. If we only had one, then how confident can we be that that's actually going to happen? So 5 is just sort of a balance between the cost of adding a repetition and the reliability that we want.
Yeah, I guess as I understood the question, that's a pretty good answer. Yeah, thanks.
So I have another question from Zebra Twist. So I don't know, since you're working with satellite question and data, it might be a bit tricky, but are changing currents linked with changing biodiversity? Do you have any insight in that?
I think so, yeah. I kind of mentioned in the beginning that eddies specifically, but ocean circulation in general, can bring things like energy and nutrients to different parts of the ocean that otherwise wouldn't get energy or nutrients. So absolutely, they can have an impact on the ecosystem that's there, and then of course biodiversity. So for example, if you have an ocean current that brings a lot of nutrients to a region, and then all of a sudden it shifts somewhere else, then that region is going to be getting either not as many or a different source or a different mix of nutrients, which can change the species that can live in that ecosystem for sure.
Yeah, that makes sense. But are there also like model data for that to say, like, with changing changing eddies due to climate change, there might be a shift in biodiversity from this point to this? So is that also focus of research at the moment?
Yes, it is. And for that, we use slightly different models. So the model that I used in the presentation today didn't include that sort of information because adding that complexity, adding another variable like, the concentration of some nutrient makes it more expensive to run the model. So definitely some people include those variables, but this simulation didn't.
Okay, we have another question from the chat from, I'm going to butcher this, in Yasik, but the question is the important part, not the name. And they noticed that the difference between the model and the observation seems to be the greatest in the Gulf Stream, and was wondering if there was a particular theory as to why it was the Gulf Stream in which the discrepancy was the greatest.
So I don't have a great theory other than that the Gulf Stream is notoriously hard to simulate, and so it might be a little bit off. As well, I talked about sort of the threshold for resolving an eddy as 1/2 of the radius of the eddy in terms of grid resolution. And so the model was sort of designed to get up to that threshold where we need it. But it's still better to exceed that threshold by as much as possible. And so we don't perfectly reproduce eddy activity in these regions, in any of the regions. And so we always expect that there will be a difference in the eddy activity that we simulate and what we observe. And in the Gulf Stream, it's more difficult than other regions.
All right. I just recognized that we lost Corinna to some kind of internet problem, it seems. But at least she was there to hear your talk and ask some questions. So it's just the three of us. And then, but I would have another question, because you mentioned the ACC, so the Antarctic Circumpolar Current, and that it will get stronger winds. And actually, so I'm looking at phytoplankton in the Southern Ocean, and also exposed the cells to different climate scenarios in bottles. And then, what the stronger winds would also have effects on the cells because they get more mixed, so they get less light over the day. But on the other hand, we also have the melting, which then would lead to more stratification. So from your point of view, can you do you have a feeling, or do you also include other variables like this freshwater input, for example?
Actually, it's a bit of a conversation in these simulations, whether the freshwater input from melting is really accurate, because some things we simulate and some things we know we don't simulate, and so we parameterize them. So we just say, well, this is how it will change in sort of a simplified sense. And so I think that these simulations don't really include that level of complexity with melting Antarctic ice.
Right. Yeah, that was cool to see, and something that I'm also concerned or looking at doing in my research. Great, thanks. Rebecca, do you have one last question?
Yes, I do actually, and we'll go back to the Arctic and Antarctic regions. Thanks, Renzi. So I know that the satellites are generally limited in their traditional trajectories. They can only get to a certain latitude before they stop reaching the Arctic and Antarctic. But in terms of your models, do you run them all the way up to 0 degrees? And if not, then is there plans to? And is there a little bit more information about how you're able to then use the more limited observations there? And of course, you have the sea ice problem as well. Like how does the model, I suppose, cope with these extreme latitudes?
Yeah, so it does go up to 90 degrees latitude in the north, not in the south, because there's land down there. Well, so in the atmosphere it does, but not in the ocean. And yeah, that is a big problem in terms of ice cover for satellites, and as well when the eddies get smaller, it's not just a problem with us simulating but also the satellite data set has a resolution as well. And so if it's too large to capture very small differences, like these very small eddies that are up near the very high latitudes, then that data isn't very high quality either. But for us, it's not really a problem that we talk about because our model resolution isn't even close to simulating eddies in the Arctic Ocean. So, yeah.
I suppose that's a relatively sort of simple solution in a way, that if you're unable to get the resolution, then maybe it doesn't matter.
Yeah, well.
That's good. No, that's good. Thank you very much.
Yeah, thanks again, also from my side, Nathan. I think I don't see any new questions in the chat, so I guess we are about to close this episode. Thanks a lot for joining us and sharing your exciting research with us. And everyone else, thanks for watching, and please also tune in 2 weeks. So next week it's a holiday, so you can all concentrate your time and energy for having being with us for the 100th episode. And I just see that Corinna might join us back for saying goodbye. So it was great having you, and see you in 2 weeks. And we just here have Corinna to say bye.
Hey.
Good to have you back.
Oh, I can say goodbye.
Yes, perfect timing.
Yeah, thanks for having me on. It was a lot of fun.
Thanks. See you.
Wissenschaft fürs Wohnzimmer.